Hello everybody, welcome back to another OpenGL stream. It has been a little over a week, but today we are going to be getting into some very exciting stuff. We're going to be learning about how to integrate physics and gravity and stuff like that into our OpenGL project through a class that we'll be calling a rigid body. So let's hop right into it. And first thing I want to do is I want to download a new model because we are going to, let me just, so we're going to be downloading a new model. The link is in the description of this video. It's just a regular sphere, and we're going to be using it as a projectile today. So just download the GLTF format, and then in here, just copy. Oh, don't buy WinRAR. So copy those two files and then go ahead and find your project and go into the assets wherever you have your models, and then just create a new folder called sphere, and then in there just go ahead and paste those two files in there. Alright, so we have those in there. Now let's just go ahead and check on what we finished off with last week. We actually did our first FPS origins. So we got a way to look down the sights of a model gun. Oh, and before we do anything else, I do want to say something first. We do have to change the size of the gun just because it's freaking massive. So let me just find the updated sizes that I have. Alright, so in gun, change the scale to 1 divided by 300.0f, and then as a result the shift is going to be smaller because we're scaling it down. So instead of 8.0 forward, it's going to be 0.5, and instead of up 3.15 or down 3.15, we're going to move it down by 0.205. Now these numbers are by trial and error. I did this just by sizing it up against a cube that was 1 by 1, so it can be kind of like 1 meter, which is kind of realistic. So if we go ahead and run this, should get pretty much the same result with this. You can see through the sights pretty close, or closer at least. Alright, so let's exit out of that. And next, let's go ahead and implement this sphere. So in main.cpp, or we actually should create the file first. So in models, go ahead and create a new class. We're going to call this sphere.hpp, and it's going to be like our other model file. So we're going to have if not defined, sphere hpp, define sphere hpp, and diff. And then in here we're going to have our include the model class, so include /model.h, and that's good for now. So let's say class sphere, and this extends public model. We're going to have public values or public methods, and all we're going to do is constructor, so sphere will be initialized with our position. So we'll start it off at the origin. The size will be 1. And that's it for now. And then in our constructor, we want to initialize the model superclass with just position and size. And we're getting more. Oh, yeah. For some reason, it takes Visual Studio a while to load the IntelliSense. Don't know why, but while we're waiting for that, if you were wondering, this is the Celeste OST, and this is by Raine, and we listened to a bit of her new Minecraft music on Tuesday. Was it Tuesday? Yeah, it was Tuesday. but she came out with a couple bangers. But yeah, okay. Now we're gonna have our init method, so void init, and this will just say load model, and we're gonna load it from the folder that we just created. So it's gonna be asset. Well, in my case, it's gonna be assets / models / sphere / scene.gltf. Oh, one thing I did forget to do is in the model, you will notice that there are no textures, it's only materials, so we have to initialize the model class by saying that no text is equal to true. Alright, this IntelliSense still isn't working. Okay, well, then let's do our render, or we actually don't need to override the render just yet, but we will. Okay, let's put this in the stupid program now. Okay, so we can actually get rid of the gun because we won't need that right now. That'll just get in the way. So we'll say we need to include the file first, actually. So just include it like you did the other models. God damn it! Why does it always default to a simp? God damn it. Sphere.hpp. All right. Now we're going to say, for the model, we're going to say sphere and sphere. Initialize it with its well, we should actually size it down. So we'll initialize it at the origin, and we'll size it down by a factor of 4. So glm vec3 0.25f. And then we'll say sphere.init. And then down in the main render method, we're going to replace the g.render with main.render, and then main.cleanup at the bottom as well. Oh, not main, sphere. Yeah, I don't know why I put main. Alright, so let's go ahead and take a look at what this looks like. Alright, so we are currently inside the sphere, but that's what it looks like. Pretty cool. I know it's pretty self-explanatory. But yeah, that's a sphere. Alright, so that is that. So now let's actually go through a little bit of physics. So in OneNote, let's go ahead and then erase all this stuff. You just don't need it. This was just me testing the other day. And the other work was from, or the other writing is from last time, I believe? Yeah, it was. Okay. Okay, God, this soundtrack is so good. It is loud, though. I will say that. Alright. So let's go ahead and start with a couple of things. So, in our physics, we are going to treat the XZ plane, so that flat plane, as we're going to kind of rotate through that. We're going to have a bunch of different coordinate systems based on the direction in which an object is moving. So, for example, we might have our unit vector. We're going back to that. So a unit vector could be like, and this is only x, y, and z, so 1 over root 2 and 0, because we're only doing the flat, the horizontal, and 1 over root 2. So this is, x is 1 over root 2 and 1 over root 2 in the z direction, and 0 in the y direction. So essentially all I want to do is just distinguish between the horizontal and the vertical plane. The reason why is because we're going to have a couple of vertical forces, gravities, if you believe in that stuff. I probably don't. I honestly don't, but you know what? For this sake, we're going to put it in there. But anyway, the way we're going to kind of talk about the coordinate system is we're just going to designate x of t as the position in that flat plane along that coordinate system. So think of the xz plane having our how do I want to explain this? Here, just think about it like this. we're going to have our x coordinates, which will actually be like an xz coordinate, and then we're going to have our y coordinates, and they're both going to be based on time. X of t can be obtained from integrating the velocity function, and the velocity function can be obtained by integrating the acceleration function. So I'll just, and then that's just some calculus physics, and then that's equal to x of t. Okay. But now if we, all right, I need to figure out how to explain this. So each position function, we're gonna think about it as being continuous. So we're gonna think about it as a smooth curve. And that the reason why is because we're only going to have definite forces acting on it. We're not going to have it. We're not going to have any portals. Well, we could, but not right now. So let's think of x of t as something like that. Now, if you zoom in enough, you'll see that it's essentially a straight line. So that's something called local linearity. Let me just actually just go on Desmos real quick. And I'll just graph arc tangent of x. Just like that. So this is kind of what I drew, but let's zoom in. And if you zoom in enough, it becomes straight. Now, if this was our velocity curve per se, and since acceleration is the derivative of velocity, if the slope of this line is constant for every small dt, so for every small delta time, now you might be seeing where I'm going with this, the acceleration is constant. We can treat it as being constant for every small interval of time, because forces don't, like if we update a force, it'll go for the next dt, but for every individual dt, the acceleration is constant, because we're assuming that you can't change forces within a dt. So you can only do it in every in the next dt. It won't be actually instantaneous. So after that, or using that, we can apply our uniformly accelerated motion equations, our UAM. There are a couple. So this is assuming that acceleration is equal to some acceleration constant. So we'll just call that AC. You know what? No, that's a bad one, because that can be mistaken for centripetal acceleration. We'll just call it A, capital A. Now, if you integrate that function, what you get is v of t is equal to v naught, the initial velocity, plus a times t. That's just simple integration. And then if you integrate that function, what you get is that x of t is equal to x naught plus v naught t plus 1/2 capital A t squared. And these are just uniformly accelerated motion equations, so you can just essentially we'll be applying these in our rigid bodies. So if x of t is equal to this function over here, and y of t is equal to the same thing, but instead it's in the y direction. So let's look at this. So x of t is equal to x naught, and remember, we're treating x as just the x in our rotated coordinate system. So it's the y-axis is going to be the only thing that stays constant in our motion, because that's the only thing that gives us like a basis point, a reference point for gravity, because gravity isn't really, it doesn't necessarily act in a different direction. It's always pointing down, and that's why we have a flat earth, because it's always just pointing down. It's not how physics works. I don't know what these freaking round earthers, what the fuck. So we can apply the x for this formula to the x here, and once again we're treating it as x and z, but it's going to be like rotated. So v, and we'll just say v x of t times t plus 1/2 a t squared, or not vx of t. I just messed that up. Sorry. Vx naught times t plus 1/2 a t squared. So where a is the acceleration, and we're going to talk about how to change acceleration and velocity, so that because they're different. there's only one way to change velocity physically, but there are a couple of different mathematical ways to justify or explain that change. Hold on, my computer is vibrating. It's making a weird noise. I feel like wait, let me just put weight on it real quick. Hold on. Okay, good. All right, and then the same thing will be in the y direction, where it's y naught plus v y naught t plus 1/2 a y t, and this has to be ax as well. So if we apply these equations, we can actually create a little model for ourselves that will represent a rigid body, and you'll see how that works. So let's go ahead and create this class. We're gonna have a new folder. So in source, let's go ahead and close out collapse the graphics and IO folders, and we're gonna create a new folder called physics. Just like that. And in physics, we're going to have our class, and we'll just create a header. So rigid body.h and rigid body.cpp. All right, now in rigid body.h, we're gonna have our macros. I'm gonna unplug my tablet real quick. Hold on. All right, so in rigid body.h, we're going to do our macro. So if not defined, rigid body h, define rigid body h, and if. And in here, we are just going to include our GLM because we're going to need vector calculations. So include glm/glm.hpp. Okay. Now in here, we're going to say class rigid body. It's going to have public members only. So the only four things that we're going to need are mass, position, velocity, and acceleration. So we're going to say float mass, GLM vec3 position, GLM vec3 velocity, and GLM vec3 acceleration. All right. Now for construction, wait, what did I? Hold on, let me just check. I have some things that don't make much sense. Oh, okay. All right, in our constructor, we're gonna say rigid body pass in mass is equal to 1.0 by default, our position, velocity, and acceleration. And these are all default values, so we'll set these to 0 by default. Oh, that's getting cut off. Yeah, all four are just set to 0.0 3D vectors by default. All right, next we're gonna have our void update, and this will just be float dt. And this will be called every iteration of the main loop, and it will update the position and velocity of the stupid thing, of the object. All right, now in rigid body.cpp, what we're going to say is include rigid body.h, and we're going to now do it with the constructor. So rigid body, and we'll do mass, position, velocity, and acceleration. And in here, oh, what did I do? We're going to initialize mass to mass, position to position, velocity to velocity, and acceleration to acceleration, just like that. And it's an empty body there. All right, now in update, we're going to say void rigid body update float dt. All right, I need to plug my stupid tablet back in just because I need to explain one more thing. Back into OneNote. Okay. So let's kind of break this down. So as t goes to 0, it becomes like a delta t, and that's what it's going to become for our project, where delta t is a small interval of time. So we're going to say x of t is equal to x of t minus delta t plus v x dt plus 1/2 a dt squared. Now, I shouldn't be using dt just because that's used for differentials, but don't think of it as a differential, or you can kind of, but it just think of it like this right now. So essentially, this is going to be our initial position. So if we have x not there, we can kind of just do a little x plus equals velocity times time, right? Velocity times dt plus 1/2 times a times t squared, or dt squared, if you can read that. But yeah, so that's how we're going to do it essentially. We're just going to do a plus equals. So we're going to say position plus equals velocity times dt plus 0.5f times acceleration times, and for dt squared we're just going to say dt times dt. Now this is kind of where I was thinking of doing that, like that rotating coordinate system. It's not going to be formally defined as a rotating coordinate system. It's just that the object is only going to be going in one direction for each sort of dt. So that's the reason why we can apply constant acceleration, and that's why we can use vectors here. So we're not really applying them separately. Like we're not really doing them separately, but that's how I was kind of thinking about it. Like the x and z, that's not going to matter too much because there's not going to be a difference between the two. Like in terms of calculations, there's going to be no difference, but with the y, it's going to have. That's just how uniformly accelerated motion kind of happens. All right, and then finally, velocity is plus equals acceleration times dt. Just like that. Okay. Now let's go ahead and try and do something with this. So I need to find. Oh, I got rid of the code I needed. Model. Okay. Alright, so let's do this. So go into your model class, open up the header and the source file, and in the header file, let's go ahead and give model a rigid body object. So we need to include that file first. So include /physics/rigidbody.h, and we're going to replace its position member with just a rigid body, because rigid body already has a position. And we'll just name it RB, not for RBs. I can assure you this is not sponsored. All right, now in model, what we're going to say is, in the constructor, it's not going to be empty anymore. Rather, we're going to just initialize rb.pose is equal to pose from the constructor. And then in render, we have to change a couple things. So if set model, we can say keep the same, but before that, we want to say rb.update dt. And dt is actually something that we'll have to pass in. So in model, we actually have to add another parameter. So float dt, and we're gonna and it's gonna give us a couple of errors because we don't pass in dt anywhere, and that has to be a required parameter. And then the only other thing we have to add is that in model, when we translate, we have to say translate to rb.pose. You know what? Let me get some rbs. All right. Here we go. What? What happened? Hold on, I'm pausing the music for half a second. The music has gotten really loud. Here we go, hold on. Is there a better one? Come on. God. There you go. That's... We have the O. That's something different, I guess. They got Barry B. Goddamn. I don't know about that one. Alright, let's resume the music. Alright. Alright, if you were confused about why I was able to do this, it's because in projectile motion problems, you usually are going to split it up into X and Y, but when you combine them in a vector, which is what we did, you can apply the different vectors, or the different components separately. So that's how that kind of worked out. Okay, now, we need to change a couple things because render is going to now need to take in an extra parameter. Alright, so, in sphere, we have to pass in dt, but where do we get dt? We already have dt from up here, from our camera. I believe it was the camera class, or the camera video. We actually implemented not an algorithm, but just a little quick method to find delta time. So all you need to do is just pass in delta time into the render function. And then we also have to change that for the other stupid functions as well. So cube needs to take in a dt in its render method. Float del dt. And then in lamp, we need to do the same exact thing. And then finally in the gun class, if you guys have that. Oh, and we also need to do this too. Okay. Yeah, just apply the float dt. And then call that at the end there. So model render dt. Okay. And then we have to change a couple things about the position. So we're just going to say rb.position and then pass in rb.position, just like that. Okay. Now we're good with that. Let's go ahead and... Is this gonna... Oh, we got another error. Oh yeah, just pass in delta time for the lamp as well. Okay, let's try this. Let's run it. It's not going to be anything different because we actually haven't applied any accelerations or anything. But you see it's still working. The positions are still being read properly. It's a nice cube. Or I just said cube. Oh my god. Okay, whatever. All right, let's now apply an acceleration. Okay, so the way to do that, or let's just set it off with gravity first. So let's actually go ahead and in physics, let's create another class. And we'll call this the environment class because this will hold a couple of values about the environment. Alright, so if not defined, environment, god damn it, h define environment h, god damn it. And if, and then in here we're going to include our vectors, so include glm slash, oh, what the fuck, slash glm.hpp, and then we're going to say class environment, and in here we're just going to have a public static glm vec3 gravitational acceleration. and then we have to define that in the source file, so you can do that either in main.cpp or in the environment.cpp. And I'm just going to do that, or I'm just going to create that file just now, just to keep everything organized. So we're going to say include environment.h, and then say glm vec3 environment : gravitational acceleration is equal to glm vec3 0.0f, and this is just a gravitational constant. It's just, you know, your constant of the acceleration due to gravity, and it's just negative 9.81 f only in the y direction. So that's why I was talking about differentiating the x, y, and z, or the x and y directions. Oh, hold on. So let's go ahead and figure out how to apply this. We can simply just do it in model. So in the model constructor, just say rb.acceleration is equal to, I need to include the environment class. So include physics/environment.h, and we're going to say the acceleration is equal to environment gravitational acceleration. Alright, now, when we run this, everything should just fall straight down. Let's see. Oh, it is. Look at that. Fucking beautiful. That's actually really fucking cool. I'm not gonna lie. Just everything falls apart. Alright. Let's get rid of that because gravity doesn't exist. You know, it's just God pulling things down by a string. That's all that's happening. Now, let's figure out how to actually change that, because gravity isn't going to be. I keep saying I'm going to act like I believe in gravity for this. Gravity is going to be the only force that isn't going to be the only force that acts. There's going to be other forces, you know, especially with our gun model. That's going to apply force, right? How does it get a bullet moving? Well, it applies a spring force that gives it velocity for some point. You know, that's pretty much how anything works, right? You touch it, you give it a force. If I smash something, it gives it a force. You know, me talking comes from a force. Everything comes from a force. So let me plug back my drawing tablet back in. I hope your headphones didn't explode from that smash. Alright, that's bright. Alright, so in here, we're going to do a couple of things. So, applying force. So in rigid body, we're going to have a couple of ways to do this. So we're simply going to have a method called apply force. And this will just take in a force, and force is a vector, so it can be applied in a different direction. It can be applied in different proportions, stuff like that. There's also going to be something called, we'll have force and acceleration, because in doing acceleration, we can kind of reduce the amount of calculations that we have to make for stuff like gravity. Like with gravity, the force of gravity, gravity is equal to mass times the acceleration due to gravity. But if you say apply force, apply the force with mass times the acceleration due to gravity, in order to talk to or change the acceleration, you're going to have to divide by mass. So it's just an unneeded calculation. And I sort of explained this earlier, but force is equal to mass times acceleration, or acceleration and force are vectors, and mass is that proportionality constant. So the acceleration due to gravity is constant. So we'll just be calling it apply acceleration, and we'll just pass in that acceleration due to gravity vector that we have, just to make things a little easier on that part. There's also two different ways that we're gonna give to apply a force, and these are gonna be stuff that you might know, stuff that you might not know. Okay, so the first thing is called impulse. And impulse is dependent on, calculates essentially, it's symbolized with J. And if you don't really know physics or don't care enough about this, don't worry about if you don't care enough, don't worry, just type the code when I do, but I'm going to explain it for those who do like this stuff. So impulse is equal to the change in momentum, and where momentum is equal to mass times velocity, and momentum and velocity are also vectors. So J is equal to the change in velocity, which is equal to the integral from t0 to t1 of f of t with respect to time. And the reason why we can do this is because force is equal to mass times acceleration, but force is also equal to the derivative of momentum with respect to time. So if we integrate it, we're going to get p of t1 minus p of t2, which is equal to delta p. Once again, that's calculus stuff. You don't really need to know. I'm just talking about it. But anyway, the way we can calculate this without doing integrals is we can just pass in a force and multiply it by delta time. Because once again, if acceleration is constant, that force is constant for that really small interval of time, that dt. And that's essentially how integrals work too. They just add very small rectangles where the force or the y-coordinate or whatever you're integrating is constant at that point. So this is also called, or more generally, it's known as the average force times the change in time. So we're going to be using a formula here. So apply impulse, and it's going to take in the force and the delta time. So and essentially, so let's look at this stuff here. So let me just write this equation out over here. So delta p is equal to p of t1 minus p of t2, or t0, is equal to force times dt. We're going to say mv1 minus mv2, just by plugging in the formula for momentum, is equal to force dt. We can just replace force with mass times acceleration. Masses cancel. And what we get is v1 is equal to v0 plus a dt. And this looks very similar to our incrementing acceleration or incrementing velocity function, because it pretty much is. It's pretty much the same thing, except it's not an acceleration. We're not changing the acceleration here. We are simply changing the mass, because impulse only acts for a small amount of time. When we're talking about apply force, we're saying this is going to be a constant force that will act on it at all times, i.e. gravity. Right, so that's the first one, or the that's impulse. And next we're going to talk about energy transfer. So energy transfer. The way we're going to do this is, when you're at the top of a hill and you, or let's say our sphere is at the top of a hill and it gets pushed, or it starts to roll down, it gains velocity. Now, if it's higher up the hill, it's going to gain more velocity. This is principle of conservation of energy, where gravitational potential energy is transferred into kinetic energy, and kinetic energy is going to be what we're going to use to calculate the velocity. So essentially, we're going to say energy, we're going to pass in a value for that energy, whether it be gravitational potential energy or spring potential energy or energy lost to friction. That's also going to reduce velocity. So anything of that sort, energy, we're going to pass in an energy. When we convert this energy into kinetic energy or take it away, it's going to be equal to 1/2 mv squared. And 1/2 mv squared, that's the kinetic energy. So essentially what we're going to want to do is we're going to want to get the change in velocity based on this equation, and then we're going to want to add or subtract based on if energy is positive or negative. So let's go ahead and actually implement all of these functions. In total, we're going to have, let me just see, we're going to have 1, 2, 3, 4, 5. All right, so we're going to have 5 functions. The reason why is because what's it called? So stupid. We want to be able to pass force in as a direction and magnitude separately, because that might be helpful in some cases. All right, so let's go ahead and start. So void apply force, and where you just pass in the 3D vector for force. Void apply force, where you pass in the direction as a vector and the magnitude as just a float. Next, we're going to do our impulse. So void apply impulse, and because impulse is it depends on force, we're going to do the force, the direction and magnitude we're going to do the force as a total and then the direction and magnitude separately. So applying impulse, we're going to say GLM vec, not ALM, GLM vec3 force and float dt, because remember it acts on a certain amount of time. And then void apply impulse, GLM vec3 direction, float magnitude, and float dt. And then finally for energy transfer, we're going to say void transfer energy, float joules. And this can be positive or negative. I believe I can get rid of my drawing tablet now. I'm hoping. I'm hoping. All right, let's define all these functions. So in rigidbody.cpp, let me just make sure I don't screw this shit up. We're going to say apply force. All we're going to say is, let me just check this to make sure. Okay, yeah, all we're going to say here is acceleration plus equals force divided by mass. And once again, that just comes from that equation where force is equal to mass times acceleration. Oh, and you need to add the class identifier. So, yeah, I forgot to do that. Ooh, there we go. Okay. And then for apply force, where we pass in direction and magnitude, we're just going to call the other apply force function, and we're going to pass in direction times magnitude. And that's essentially the reason why we're doing these two functions, to give the programmer a little more freedom in what they can choose to write. All right, next for impulse, so we're going to use our formula that we derived up here, where force, remember VO, so we can just replace this with the plus equals acceleration times delta time, but because we pass in a force, we're going to say velocity plus equals force divided by mass times dt. And then for the direction and magnitude, we're going to say we're going to say apply impulse, where the force is direction times magnitude, just like before, and we're going to pass in dt as well. Okay. Now for the last one, we're going to say transfer energy. And for transfer energy, what we're going to say is if joules is equal to 0, we're just going to return. And that may happen depending on, because we may end up performing some calculations during each iteration and they might return 0. Like with friction, you might not be moving, so it might give you a 0 energy transferred out of the system because you're not moving. So kinetic friction cannot act. Next, we're going to calculate our change in velocity, which is just from this equation. It's just some simple algebra. So we're going to say comes from formula ke is equal to 1/2 times m times v squared. And we're going to say float delta v is equal to the square root. So I do need to, I've been using a lot of delta v's and plus equals a lot. That's just because, once again, the dt is so small that we can just consider everything as a really small change as well. So we're just considering the change in something. We're not hard setting the velocity. We're just actually we're calculating the change here, because once again, if we were hard setting something, that wouldn't naturally align with, or that wouldn't align with what naturally happens. So we're going to say square root of 2 times the absolute value of the joules, because if joules is negative, you're going to get a negative value, which you can't square root that. So we're going to get the absolute value, and then we're going to say divided by mass. Next, we're going to say velocity. So now we are adding in the change. So velocity plus equals, and we're going to do a ternary operator here. So if joules is positive, that means work was done on the system. So if joules is greater than 0, then we're going to say add delta V. Otherwise, add the negative delta V. All right, so let's see how this is going to work. If we how should we test this out? Did we get rid of the gravity shit? Because I just want to make sure that's not still there. Yeah, okay. Let's see something here. Oh, we also didn't do the apply accelerator, did we? No, we didn't. Okay, yeah. So just in rigid body, you don't have to do this if you don't want to. But just add 2 functions. They're going to be pretty much identical to the apply force. Just do apply acceleration and apply acceleration with direction and magnitude. And then change that to acceleration. And then in rigidbody.cpp, definitions for these are just going to be acceleration plus equals the acceleration. We're not going to divide it by mass this time. And then add your tags there. I have that on insert for some reason. All right, so we're going to say acceleration plus equals accelerate. Just change it to A, just so we don't get naming conflicts. So acceleration plus equals A, and otherwise we're going to say apply acceleration direction times magnitude. And just notice once again how we don't divide it by mass, because we're applying an acceleration like gravity to reduce unnecessary calculations if the acceleration is constant for all objects, no matter their mass, like gravity is. Okay, so let's go ahead and let's actually integrate something with a keyboard input. So in order to do that, we have to make this sphere a global object. So we're going to say we're just going to move this sphere declaration to outside the main loop, or the main function. And then in process input, what we're going to say is if let's say keyboard key went down, glfw key L, let's say sphere.rb, because we're accessing the rigid body class. We're going to say dot apply impulse. Let's say the force is, or let's do a magnitude and direction. So let's say the direction is the camera direction. So camera, default camera, dot camera front. Then the magnitude will be, let's say 5.0f, and dt will be delta time, which we pass into the chain or process input function. So let's go ahead and run this and see how it works. All right, so nothing is falling because we don't do any gravity. So let's press F. Something's not working. Maybe 5 is too little. Let me try. You know what? 5 is too little. Or wait, no. Because we don't set a mass, that's why. That is exactly why. I ran into this problem earlier where velocity was becoming like a negative infinity, or NaN, because mass is 0. So if force divided by mass, you're going to get some constant divided by 0, and that's not going to give you anything. So we have to say, in rigid body, or no, don't we set the mass? I thought we did. Model. Here, let's just try setting the mass to 1 in the sphere. So rb.mass is equal to 1.0f. Let's see if that works now. Alright, now let's try increasing the force a little bit. Let's try doing 5,000. Nope. Something's wrong. Alright. Oh god. Alright, let me check my code. Let me just put a breakpoint here so I can just see if that. Oh, because I was putting. Oh no, because I set this to L and not F. I'm an idiot. God damn it. Right? Yeah, because L is for the flashlight. That's something different. I'm an idiot. There you go. Look at that. Just freaking launched. And it goes out of view because we don't see it anymore. God damn, that was just fucking launched. Did you see that? God damn. Alright, now I need to find... let's try decreasing that a little bit. Let's say it's 1,000. And then we have to put in gravity someplace so we can actually look at how a little bit of projectile motion per se, don't we? Okay. Where did I put in gravity? Where do I set gravity, actually? That's a really good question. Is it in main? I'm just looking at my code now because I just want to see. Yeah, it probably is main. Yeah, it is. Okay. Alright, so all we gotta do is just, when we initialize this sphere, let's just say sphere.rb.apply acceleration, and once again, because it's always going to be there, so we just want to put it for now. We're going to say environment. Oh, I don't include it, so we need to include the environment class as well. So include physics/environment, and say environment gravitational acceleration. And now let's see how this works. Right. Oh god! Oh, because it just dropped, didn't it? Yeah, that's going to be a problem because we don't really see how the shit works. Okay. Well, let's try something out here. Let's create a vector of launch items. So every time we press F, let's call a function called launch item, which we'll create right now. Void launch item. And let's put that not there anymore. Let's see. Let's go ahead and create a vector of spheres up top. So instead of having sphere here, we're going to say standard vector of sphere, and we'll call this launch objects. And in launch objects, or let's just go ahead and iterate through it. So every time we launch an item, let's say sphere, new sphere, and we'll initialize it with a position. Let me just make sure I'm getting this right. Position and size. So position is camera, default camera dot camera pose, and size is glm vec3 0.25f, and then new sphere dot init, and then we're going to say new sphere dot rb dot apply acceleration and environment gravitational acceleration, and then we're going to do our impulse where we shoot it. So new sphere dot rb dot apply impulse, and we're going to pass in direction as camera, default camera dot camera front, and the direction is, or the magnitude we'll say is 5,000 or 1,000 we said, and then dt is just delta time, which we have to pass into this. So launch item takes in dt, or delta time. I should honestly standardize that. I can do that later. All right. Now let's just add it to the list. So launch objects dot pushback new sphere. And now in order to actually iterate through all these, let's go ahead and in the main loop, let's say under where we set the view and projection in the main, for the main shader, we're going to say for sphere, or let's say for sphere S, or sphere in the launch objects, let's just call sphere.render, pass in shader, dt, and set model as true for that. Or delta time rather. You know what, just do a quick find and replace for delta time and change it to dt. Just because I'm gonna get pissed off with this. Okay. Hopefully there are no errors with that. Alright, and then let's do the same thing with the cleanup at the end. Alright, and let's see how this is going to look. Alright, so no sphere on the screen yet. I'm going to press F. Oh, I know what's wrong. Make that a reference. I was getting this stupid fucking problem in testing just because of, I don't know, it got stupid annoying. Because the rigid body wasn't getting updated properly every time for some stupid reason, so it was just vibrating back and forth. So let's just now try it and press F and you shoot it. Look at that projectile. That's actually pretty sick. I won't lie. Ah, nice. And what you will notice is that if you look on the far right of the screen, as I am shooting more objects, the memory this program is using is increasing drastically. Like, look at that. Every time it's increasing by 1 or 2 megabytes. And the reason why is because we are creating a new sphere object for every single object we launch, and therefore it's loading in a new sphere object every time. So it's loading in that 1 or 2 megabytes of the file, of the object file, every single time. Now, in order to combat this, we're going to create something called a model array. Now, I pulled that name straight out of my ass, but it gets the job done because it makes sense. We're going to create a template class that will allow us to load a model in once, and then just duplicate and render it several different times on the screen for every time that we want it to be displayed. So in models, go ahead and create a new file and call it modelarray.hpp. So modelarray.hpp. Let me just get my code out. Okay. We're going to do our macro, so if not defined, model array hpp, define model array hpp, and then end if. We're going to include model, so include /model.h, and then we're going to say template class t, class model array, and we're going to say public. Now, in order to have a bunch of different instances of an object without loading the model in separate times, the one thing that differentiates all of these objects, not their model, is going to be the rigid body. So their positions are going to be different. So therefore, instead of having a vector of models, we're going to have a vector of rigid bodies. So we're going to say standard vector rigid body instances. Oh, is this the best part? Oh, it is. This is the fucking part that just slaps. Holy crap. I'm gonna turn this up just a little bit. I hope you guys can hear that. I don't know. Alright, so in here we're gonna have our void init, and we'll define that later. Let's actually create our what we're gonna use in that, and it's gonna be a protected, and it's gonna be T model, not model T. Henry Ford didn't create this. Is that his name, Henry Ford? Yeah, I think it is. This isn't model T. This is T, the class that we're passing into the template. So that can be a sphere, it can be a lamp, it can be something, it can be this, it can be that, it can be a fat dildo, but you know, that's besides the point. That would actually be interesting to see if I could put that on YouTube. Just like a purple big dragon dildo. I don't know. I doubt that they would allow that. I would just get banned immediately. Okay, so for init, we're just going to initialize the model just like that. And the optimization that we get here is that we're only initializing it the one time. Now, what we aren't initializing one time is the rigid body, which we will be adding separately. So we're going to say now in void render shader float dt. We're going to say for rigid body RB in instances. We're going to say rb.update dt, and then model.rb.pose is equal to rb.pose. All this is saying is just update the position of the model to the current rigid body that we are iterating through. And we can't like create we could create an array in the model, but we're just going to do this now because we don't always want to have an array of models. We might, like for the gun that we have, we only want one of those guns. So that's how that is going to work. I think this just makes a little more sense than kind of combining everything in one class and making it a little more confusing. And then in here we're just going to say model.render pass in shader and dt, and the position will be updated to the rigid body that we are iterating through. Now the one problem with this is what we ran into last time is that we need to pass in the reference. So the reason why we do this is because when we call update, if we don't pass in a reference, we are updating a copy of that rigid body. So by passing in a reference, we are updating that specific actual rigid body, and that update will stay with it. All right, here's the fucking sick part of this song. Holy crap! I might just not talk for a little bit, but I'll let this ride out for a second. Alright, I'm just going to add two methods, set size and cleanup. They're pretty self-explanatory, just copy what I put on the screen. I just want to listen to this shit. Alright, I'll call it continue for now, unfortunately. I can't just sit here forever. Alright, now let's go ahead and actually use this. Going back into sphere, and let's just create this sphere array in that sphere file. So just go ahead and do class sphere. Alright, let me turn this down a little more. It's kind of loud. So sphere array extends from public model array, and since we need to pass in a template, we're going to say model array of sphere. And in here we're going to say public, and the only thing we need to change about this one is void init. And all it's going to do is just model is equal to sphere glm vec3 2.0f and glm vec3 0.25f. That was the really good part, by the way. It's not much, but it slapped a lot. So the reason why we're doing this is just because this is just like any other model that inherits from the model class. We're just changing the initialization code because we don't want to initialize it using some stupid shit. We want to initialize it using the actual model that or the model file that we tell it to. Alright, so now let's actually try and put this into our main class. So up top, get rid of the vector or the sphere array, and we're just gonna replace that with sphere array launch objects. And now down in models, we're gonna say launch objects.init. Just like that. I'm just making sure I'm not skipping anything. Alright, and now let's go ahead and actually render this shit. So we actually don't need to iterate through anything because that render method is already in there. We already iterate through all the rigid bodies. So all we're just going to check to see is that if the size, if there's more than one instance in there, and we're just going to render it, just because we don't want to call the method if there's nothing to render. So we're going to say if launch objects.instances.size is greater than 0, launch objects.render shader and delta time. Something's wrong. Oh, I didn't even include it. So in sphere you need to include the file model array.hpp. That's why. That's the reason. Okay. Alright, so now this should all be good. And it's DT because we changed that. Alright, so and then after that, let's just do for cleanup we're just gonna say launch objects.cleanup. And then the next thing, or the final thing that we've changed is the launch item. Because instead of initializing a new sphere, we're going to initialize a new rigid body. So rigid body RB, we're going to initialize it with a mass of 1.0f and a position of camera, default camera.camera position, and we're going to say rb.apply impulse camera default camera front, and I think we did 1000 for the magnitude, and we're going to pass in dt, and then we're going to do the gravitational acceleration. So rb to apply acceleration, environment gravitational acceleration, and then finally we're going to add this rigid body to the launch object. So we're going to say launch objects dot instances dot push back RB. Alright, now let's run this and see how it works. Nope. Alright, so keep an eye on the memory. No increases. I'm still launching shit. No increases. I mean, eventually at some point there are going to be increases because enough rigid bodies will cause an increase, but look at all that shit. That's pretty cool, right? I mean, we could increase this force just to have fucking zoom. Let's do 10,000. Oh. Oh! God damn. And you do see that the lighting does change. Like, it's really bright and then it's dark. Because it's far away. And that's pretty cool. So the lighting does change, so you know that the fragment shaders are working, the new positions are working, stuff like that. This is, I could do this all fucking day. This is pretty sick. I won't lie, this is pretty sick. Okay, that's pretty much the main part of what I wanted to do today. The next thing is I want to apply this model array to our lamps, just because we do the same thing with the lamps, so I just want to change it just a tad. So in lamp, or open up the lamp class, and we're going to do the exact same thing that we did with the sphere, but it's just going to be a tad different. So we're going to include model array.hpp, and then the class will be at the bottom. So let me just open it up over here. All right, so class lamp array extends from public model array, and it's going to take in lamp as its template because it's going to be an array of lamps. Now, the next thing that we're going to do is we are going to, instead of doing a rigid body instance array, we're going to do a point light instance array. Now, this point light comes from that structure that we did in light.h. So this one, so point light right here, because that has position in it. And we're not going to apply any motion to the lamps yet, but we may in the future. So for now, I'm just going to change it to standard vector of point light and light instances. And for init, we're going to have our different shit. So void init, and we're going to say, how do I want to do this? Model, this code is going to be really inefficient. I'm going to tell you that right now, because we're going to be initializing the same thing several times. So just take the code from the main class where we pass in or initialize the lamps, or so the point light value. So copy that and just put that in here. And so model is equal to that. And then instead of point light positions at I, just initialize it to glm vec3 0.0f. Just like that. And then after that, just do model.init. And then for render, since we don't have rigid bodies, we're going to have to initialize it with the position from the point light. So we're going to say void render shader float dt. So for point light pl in light instances, we're going to say model.rb.pose is equal to pl.position, and then model.render shader dt. So it's pretty much the same thing, except we're just changing the source of the position. I hope that makes some sense. Now, in the future, the way I see applying physics to these lamps is we just create or make point light into a class and have it extend from rigid body, so it can still be considered a rigid body and we can still apply impulses and shit like that to it. So because that's where I just see this going. All right, so that's the thing that we have to change in lamp. Now in main, we're gonna have to initialize the lamps in a little different way. So in main, we have our point light positions. Let me just see how I do it over here. Okay, so I'm gonna have a some default values for the ambient, diffuse, specular values, and there are light constants, just because they're going to be the same for all four of the lamps. And I can replace that in here just to show you guys what that would look like. So we're going to say glm vec4, because remember we're doing 4D vectors for the colors. Ambient is equal to glm vec4 0.05f. 0.05f is 0.05f and 1.0f. glm vec4 diffuse is equal to glm vec4 0.08 or 0.8f, 0.8f and 0.8f, and then 1.0f, and then glm vec4 specular is equal to glm vec4 1.0f just entirely. And then our constants, we're going to say float k0 is equal to 1.0f, float k1 is equal to 0.09f, and float k2 is equal to 0.032f. Alright, now... Oh, shit. I just finished my water. I'm gonna try and power through this. Alright. So the way that would change initialization is we're just gonna change all those vector values to ambient, diffuse, and specular, and then... Oh, what just happened? Oh. And then, K0, K1, and K2. Just like that. So that's how that would kind of change it. Now, we're going to do pretty much the same thing. Let me just see how I do this. Alright, so now let's go ahead and create our lamp array, and we don't need any extra includes because that's already in the lamp class. So we're going to say lamp array lamps. You can just comment out this array over here. And we're going to say lamps.init, and then for unsigned int I is equal to 0, I is less than point light positions dot size. That works, right? No. Oh, no. Just I is less than 4. It's not a vector, so it's an array, so we can do that. And I++. Oh, I put an extra parentheses, or parenthesis in there. Alright, now in E... What's going on? Oh, yeah. Make sure that you set all this stuff to public in the lamp array, because then it's inaccessible. Alright. Now for each lamp, we're essentially going to be doing what we did up there, and we're going to be saying, how do I want to do this? Alright, so lamps.lightInstances.pushback, and we're going to initialize each point light, and since it's a structure, we can use an array initializer list, so we're going to use pretty much what we have up here. So in parentheses or curly braces, we're going to say point light positions at I, then K0, K1, and K2 for our constants, and then ambient, diffuse, and specular. Right? Yeah, that's how that's going to work. And then we just got to render this shit. So in... Oh, some shit's wrong. What's, Did I forget a semicolon up here? No. I probably did. What? This declaration has no... Oh, did I delete main J? No, I didn't. What the fuck is going on? Alright, let's just try and do this, and it's going to give us an error, but let's just try. And then all we got to do instead of doing the loop is we're just going to say lamps.render, pass in the light shader this time, and DT. And then for the cleanup, it's just going to be lamps.cleanup. Alright, let's run this and see what's wrong. Alright, is there anything outside of main.cpp? No. Still got 20 minutes on this, alright, we're all good. Alright, 1 second. Let me just send a text real quick. Oh, come on. Alright, what's wrong with this shit? It has to do with something that I wrote right here. Oh, I put an extra curly brace, that's why. Okay. Now everything's fixed. Right? Oh. Hold on. Now that all those errors are out of the way, we get to change a couple of other things. Instead of doing the lamps.i.pointLight, we're gonna say lamps.light instances at i.render shader I, just because we want to render each lamp position into its into the shader. And then down here, oh, it's lamp shader. Okay, now this should all work. I'm hoping. Aha! They are still there in their respective positions, and we are just launching shit. Holy crap. Yeah, okay. The last thing I want to do before we bring the gun back in and kind of make it like a bullet, because I know someone was asking about that in a previous video. We're just going to add just a little more memory optimization, where we remove objects that are really far away from the camera. So all we're going to do for that is we're going to create a stack of integers for the remove objects, and we'll see why. So we just have to include stack. So include vector, I guess we didn't have vector included. Just include stack. Alright, now in the main loop, we are going to say, where am I? Okay, so right above where we say launch objects.render, we're going to say sc stack of integer remove objects, and we're going to say for int I is equal to 0, I is less than launch objects dot size I plus plus. We're going to say, so if the distance between the camera and the launch object is greater than some value, we're just going to remove it. Launch objects dot instances dot size. So all we're going to say for this is if glm length of camera default camera dot camera position minus launch objects dot instances at I dot position. That just gets the vector between the two, which is essentially the distance, and then we take the length of that vector to get the magnitude of the distance. So if that is greater than, let's just say, let's start it out at 300 so we can see the difference. So if it's greater than 300, then we just want to say remove objects dot push I, and then we're going to say continue. Now after this, we want to say we're going to iterate through each integer in the remove objects. So for int I is equal to 0, I is less than I is equal to 0, I is less than remove objects dot size I plus plus. So what we're going to say now is launch objects dot instances dot erase. We're going to get the beginning iterator and then add some index. So launch objects dot instances dot begin. So that's the beginning iterator, and then we're going to add an index. And we're going to say remove objects dot top. Now this is why we were using a stack, because if we used a vector and we started from the beginning of the vector, and let's say that we had five launch objects in there, and the first object was let's say the first object was, the first and a second object were really far away. So if we erased the first, or if we marked the first and second objects for removal, and we iterated through that from the bottom, we're going to say erase the first object, but now the second object becomes that first object. So when we say erase the object at index 2, we're actually erasing the third original object. So we're going to be erasing the wrong object. So we didn't want to go top to bottom, remove the last objects first. So launch objects like that, and then we just want to pop that from the stack. So we're going to say remove objects dot pop. We've done a little bit of stack stuff in the shunting yard algorithm when we did that like 2 weeks ago, I believe. But that was that we used stacks then. So let's actually see how this looks. So 300 is our removal distance, and we'll see how that looks. So it doesn't look too different from before, but now let's change it to, let's say, 50.0f. And let's look. See, it goes away much quicker because that's 50 units away. So we want it to mark removal. So it's just like that. Okay. I pretty much have nothing else to say. Got through all that. Let's see, how long did that take? Hour and a half? Pretty good. Yeah, I mean, we got nothing else. It's been pretty, I don't fucking know. This was fun, actually. If you want to add the gun back in, you can just look at the code from the beginning. I'm not going to do that because I'm too lazy right now. But yeah, that's an introduction to physics. We'll be looking at more applications of this in the future, and then at some point, if I actually manage to learn this, collisions, that's going to be something very difficult, very math intensive. I might wait until I know math, like more math, to do that, because that might be a doozy. But I don't know. We might end up using a collision library, but I don't know. I don't really like using libraries that do a lot of the work for us. I mean, we are using libraries here, but that's mainly just math and image libraries. The math is just stuff that we've already been over, so and it would be tedious to write. And then the image, that's not really too important to what we're doing. I'm focusing more on the GPU side of things. God, this is repeating, isn't it? Alright, anyway, I got nothing else to say. I'll see you whenever. I don't know, I might come back next Tuesday where we'll, I actually have an idea for a new algorithm. It's called the quadri algorithm. That'll allow us to store objects in like a quadri, and I'll explain more about that later. But maybe we'll do that, I don't know. Anyway, that's pretty much it. I will see you guys whenever. I hope you enjoyed watching, and before I forget to say, I really do need to thank you guys for the support. We're almost at, 100 subscribers? That's pretty fucking sick. I won't lie. Dude, it is pretty fucking sick. But yeah, anyway, I'll see you guys probably Tuesday, I don't know. But anyway, goodbye. Yeah.